So a superconductor is just like gold, just like copper. Well, it has a property just like copper, so they can conduct electricity. But you know, just like heroes and superheroes, there's a hero and they're pretty good at what they do, but the superhero is, of course, it's better, right? It's the superhero has to be better. So if I take a material that's called a superconductor, well, that can be a superconductor, something like this, then maybe we can see also some super cool effects. However, if I take this tube, I still have it here. If I take the tube, I take the magnet, and I throw it through this tube. 3, 2, 1. Nothing really happens, right? And that's because this superconductor only becomes super under very certain conditions. And these conditions, well, they are very, very close to Switzerland here. It has to be really, really cold. But just cold, like 0 degrees, is not enough. What I actually need is a super cool liquid. Here it says Stickstoff because we have it written in German because Switzerland has 4 different languages. One of them is German. And here it says Stickstoff, which in English would mean nitrogen. Actually, here inside I have liquid nitrogen that boils at minus 196 degrees. Yeah, you heard that right. It's almost minus 200 degrees Celsius. So it's an extremely, extremely cold liquid. So I will now try to cool this tube down with this liquid nitrogen. You can almost see also on camera the liquid moving slightly. That's because it really starts boiling when it comes to contact with something that is on room temperature. So different things have different boiling points, and liquid nitrogen has, of course, a very low one. So as soon as this stops boiling, we know that the tube is actually cold enough. So now I will take this tube carefully, hold it like this. Oh, first I have a question for you. If I cool down this cylinder, this tube, and I throw the magnet through it, what do you think will happen to this magnet? Are we ready? 3, 2, 1. Wow, can you see that? Let me cool it down a bit for you as well. Can you see the magnet is actually stuck? It does not fall through. As soon as the tube warms up, of course, the magnet will fall through. But when the tube is cold, the magnet stays in place. It stays on the top of the tube. So this is because of the special condition that happens inside this tube. So this tube is a superconductor, and it becomes superconducting only when it cools down. That's why we call this a special state of matter. So when we talk about state of matters, usually we talk about a solid, a liquid, and gas. But this one is one of the ones that we usually don't talk about, but there's plenty out there. We have superconductors, we have plasma, etc., etc. Superconductors can be very, very, very useful. But of course, the tube is only one way to show what a superconductor can do. Another way of doing this is by having, well, you know, a disc plate. This is a regular disc plate, and it's made of a similar, well, of the same material as the tube before. So it's made out of a ceramic that becomes superconducting when we cool it down. It might actually be easier if I just take this one because we have more liquid nitrogen here. So This thing is now gonna stick to the surface. That's the first thing that's gonna do. And now it's gonna cool down in here. And when it cools down, it will get a very special property that we call superconductivity. And of course, we know that through this disk, we cannot make the magnet fall, right? The magnet won't fall through this. There's no way that it will happen because it's solid. Although it's superconducting, it's still solid. Nothing can go through it. But once this cools down enough, what we can do is we can put a magnet on top and see what happens. If it's going to be anything like it was before, well, the magnet will start misbehaving. See? Every time I want to drop it on top of this, it starts misbehaving, and it is pushed away. Not kidding, I'm not throwing this away. It's really misbehaving a lot. But this doesn't matter. So now I always put it upside down. And you would say, of course, because magnets, you know, when you put them the same side and the same side together, they will repel. Let me try doing it upside down. Let's see what happens now. With a regular magnet, if this would be just a magnetic field, we would see that, of course, they would go together. But here, you can see it actually pushes it up and away. So superconductors actually behave in a way that they expel any magnetic field. They throw it out. They just don't want to do anything with magnetic field. They hate it. Unless they're a very specific type of a superconductor. And for this, I'm going to show you a different experiment. And I will need to move my camera, so you will not see me anymore. I'm sorry. But you will see this fantastic little train. So we made a train out of with a 3D printer. It even has a nice smiley here. So this train, inside, it has a superconducting plate, the same one as we did see just now. So now I'm going to put it on two tiny plates, and I'm going to cool it down again. And because this is going to be cooling down for quite a while, I have plenty of time to explain actually what is happening inside these disks as well. So because superconductors are such good conductors, whenever we come close with a magnet, we have inside these superconductors basically an electric current that goes around. And this electric current then acts like an electromagnet. That's why it pushes the other magnet away. If I just go with a plastic plate next to it, nothing will happen. But when I move a magnet next to it, then things start to happen. But what is happening with the train at the moment is that this train is on a track. So you can see this track, and this entire track is made out of regular magnets. So that kind of magnets that we saw before, they are just put around on a track. And we are cooling this train down now. And while it is cooling down, of course, we have the same hate towards the magnets, but they kind of learn to love each other as well. So they kind of don't want to be together, but still they stick together a bit. So they're basically socially distancing, the same way as we do now during these COVID times. Okay, and our train is now ready. I will just cover it up, show you on camera how it actually looks like. Ta-da. Okay, and now let's take these plates out. You don't need the plates anymore. Look at the train go. And this train will continue to go in circles until air resistance slows it down, because there is no other resistance at this point than, of course, the air resistance. There's no traction because it is on a tiny air pillow. So it really is traveling around on an air pillow. And if we go like this, we can see it from afar, traveling really above these tracks. It's starting to shake now. That's because, of course, the magnetic field on the track is not completely perfect. That's why it starts shaking, because it's like, I don't like all of you guys, but some of you, I tolerate. Of course, as long as this superconductor stays cool, we can use it as, of course, we can see it in the chat as well, kind of like a hovercraft. But the same principle is actually used in maglevs, so in the super fast trains that we hear about in Asia. But superconductors itself are also useful for making another thing go in circles like this. And it's not a train, it's actually what trains are made of. At CERN, we use superconductors to make the smallest particles of matter that build an atom, so protons, not really the smallest, but one of the smallest, go around in circles, and that helps us do our research.